Thank you so much for Tony's nice introduction. And I would like to start with, it is my great honor to be selected as one of the finalists of this year's Poul Harremoës Award, with the other two candidates, Vincent and Welcome. And I'm also very happy that I had a chance to present this study, detecting urban illicit discharges by using an army of low-cost sensors to all of you, including the panel members and the audience. I hope you will enjoy this presentation. I only got 20 minutes, so let's get started. So conventionally, in our urban separated stormwater sewer networks, we consider surface runoffs during wet weather events are the major source of pollutions to the downstream natural waterways. However, that's actually not the full story. During no matter dry or wet weather period, we also have many other illicit discharges that can enter into our drainage network. That's including surface dumping and spills, direct cross connections from residential, commercial, and industrial properties, exfiltration and overflow from the sewer network, and also leaking septics. Due to the poor water quality of these illicit discharge sources, they can potentially pose a severe impact on the downstream waterway health, aquatic lives, and human beings. So the video here basically shows you a foam event that actually occurred in Melbourne back to 2018 at Dandenong Creek, which basically shows you how bad the situation was in the city I currently live in. And also it emphasized the importance for us to resolve this problem to address the concern of the general community about our waterway health. So in the past, we have tried many other detection methods, such as visual inspections, data testing, smoke testing, and also in-drain CCTV cameras. However, all of these techniques, they tend to have some limitations. For example, the visual inspections could be quite subjective. Both dye testing and smoke testing could have quite limited usage. Take dye testing here as an example. It pretty much only works for detecting direct cross connections, and it also requires field crews to get into individual private properties to conduct a test, which is actually a physical barrier. And all of these techniques, they tend to be very labor intensive, which means it could be quite useful at a small scale on a single street with 10 or 20 properties. But if you want to upscale this to a whole urban catchment, I want to detect all illicit discharges happening in the region, they all tend to have very poor spatial and temporal coverage. So in consequences, from previous studies and reports, we know that many dry-weather illicit discharges were not able to be detected, especially for discharges with short flow duration and occurred during after hours. And as a result of that, we currently have quite limited knowledge about the characteristics, or we'll call it the nature, of illicit discharge issues, including the key questions like where are they? Where do they tend to occur? What is their discharge frequency and duration? And are there any specific discharge patterns? For example, whether they tend to occur on a specific day of the week. So in order to overcome these issues and answer these questions, we here, or BOSO team, we look into this concept and propose this next generation sensor army. So our concept is simple, right? Field crews, they cannot be at the field to do the detection work all the time, but our sensors can. And visual inspections tend to be subjective, but our sensors are not. So if we can install as many sensors as possible into our drainage network, we would then get a very good chance and to achieve a very high visibility of the infrastructure and to potentially detect all illicit discharge activities inside our drainage network. But can we use these high-end industry standard techniques? For those of you who have done lots of stormwater or wastewater, natural waterway monitorings, you must be very familiar with that already, and you get the answer straight away. And the answer is no, they are too expensive. We cannot afford them for the purpose of this study as a proof of concept work. And also the final end users of our next generation sensor army, like local councils, EPA, and water authorities, they won't be able to afford it to install hundreds and thousands of these kind of high-end sensors and loggers into the drainage network for detecting illicit discharge purpose. So at here, our BOSO team, we took this challenge. We developed our own Arduino-based data logger. We call it the BOSO board. Instead of doing the same thing as the old school technologies, we also integrate into this NB-IoT, narrowband Internet of Things technology, onto our data logger. The good thing about here is we can actually upload our sensor readings to our nominated website in real time. And by doing that, we have lots of benefits, like You don't have to physically go out there to so many sites to collect your data anymore. And also, previously, if we're using conventional data loggers, you won't be able to notice if your sensors are dead or anything goes wrong. But now with our real-time sensing logging, you can actually notice all of that when you are watching Netflix, the next episode of Squid Game at home. Apart from that, we also introduced our own all-in-one sensor that can adequately measure water level, electrical conductivity, EC, and temperature. I won't go into too much detail about that. That's not the main purpose of my today's presentation. But I can tell you that we have tested this sensor both under the lab condition and out in the field, even under 3 meters of water. And we can confirm it works perfectly well, more than capable for the purpose of illicit discharge detection purpose. If you want to know more about our sensor design and our work, feel free to go on this MDPI Sensors Journal and have a look. And in total, with our both board or sensor, a battery that can supply the whole unit for half year's battery life, the whole unit only costs roughly $150 US. Sorry guys, our price, the cost went up a little bit due to this pandemic, this global shortage of electrical components. But if you compare with old school conventional technologies, we're still running on almost like a 95% to 98% discount. And another key thing I want to mention here is our installation methods. Like, in order to make our low-cost sensor army really low cost, we cannot afford to do confined space entry. I don't know what's the rules in your country, but here, down here in the country, Australia, if we do confined space entry to install these sensors, that will roughly take us minimum like 2 to 3 hours at each site. So what we propose here in this study is simply attach the sensor either to a sandbag or to a steel or aluminum pole, drop the sensor to the invert of the pipe, secure or ropes and steel poles on the top of the pit into the concrete. And then both of these methods only take us roughly 30 minutes to install and take you roughly only 5 minutes to take it out if the sensor is dead or you need to do the maintenance. So now we have our sensors, loggers, and installation ready. We can put them out into one of our case study, and our sensors will keep just busy doing the hard work for us, and all the real-time data will be uploaded to our online cloud database, and all the magic happens here at the backstage of our super-duper cloud computing algorithms. And we basically are here, we clean all of our data set, get rid of all the poor quality data period, split the data set between wet and dry weather period, and look into the dry weather period to searching for the illicit discharges. Don't get me wrong, like we also have illicit discharges during wet weather events, but they just mix with the large volume of surface runoffs, so we won't be able to detect them. And once our super duper algorithms told us, hey, dude, we found some interesting anomalous dry weather discharge activities, real-time alarm will be sent out to our field crews or to us, so we can quickly go out there to inspect the site, to conduct some water quality indicator monitoring to understand how harmful the discharge is, and also get the chance to track back to the source of the discharge activities. And another important thing here is with all the data we collected with our local sensor armies, we get a very good chance to understand the nature, the characteristic of this problem, illicit discharges in our urban drainage network. So now we bring this concept out to one of our case studies, Ojo's Creek. Ojo's Creek is the subcatchment of Dandenong Creek I mentioned at the beginning of this presentation. So due to the large number of industrial activities in Ojo's Creek, it was previously been identified as the potential source of illicit discharges that caused the downstream foam event. So in total, we installed 22 sensors in this area for 1 year-long monitoring. And we have 17 sensors for targeting the industrial activities in the region, which shown at this red cross. And we will also install 5 sensors for targeting the residential and commercial land uses, showing as the yellow star on this map. So here, now we have our dry weather period data. Our algorithms, also pre-tested algorithms, also help us distinguish the discharge into 3 types of conditions. The first type of condition, we call it no discharge. Basically, our sensor reads 0 water level and 0 electrical conductivity level, which is what we want, right? That's the case. That's the clean side with no flow running in the drainage pipe at all. And the second type, we call it continuous flow, which basically shows a pretty steady level of water and quite stable level of electrical conductivity as well. So this kind of continuous flow could be caused by cooling water or a blocked pipe. I'm not saying they are not important. They're still quite important and needs to be inspected. But what we are most interested in and want to understand is this dry weather discharge pulses. They started with no discharge or continuous flow, and suddenly the water level go up. And after a period of time, the water level come back. Such a pattern basically tells us it could be potentially caused by some, unauthorized usage of drainage networks and linked to human-driven illicit discharge activities. So we checked all of our site, and the results here shows you the percentage time of each type of discharge conditions at all of our monitoring site. So the first thing you can see here is we have no sites are 100% green. So there are no green lights for all the sites we monitored. They all tend to have some kind of dry weather discharge activities in there. But we also observed quite significant variability between our monitoring sites. For sites like IND 04, 05, and 06, during most of the time, if you go to visit the site, you will see dry weather discharges running in there. But for site like IND 01, during 75% of the time, they're actually clean, and only 25% with continuous flow. So pretty good job to the industrial activities in here. They pretty much didn't do anything wrong to our natural waterway health. So as I mentioned, we really want to look into these dry weather discharge pulses period, because it potentially has very high level of pollution concentrations, and they will pose significant impact to the downstream. So there are two sites I really want you to remember and follow these, take it to the following of this presentation. They are IND 05 with 11% of the time, and IND 13 with 7% of the time that covered by dry weather discharge pulses. So we further look into the characteristic of these pulses. And the figure here shows you in total how many number of pulses we have detected per year for all of the monitor sites. And in average, for industrial activities, that's roughly 160 pulses per year. And for residential and commercial activities, that's roughly 80 pulses per year. And as I mentioned, you can see IND 05 and IND 13, they both almost get 1 pulse per day. This significantly indicating that something was going on at these two locations, and we really need to quickly find out what is going on there. And for some other sites here in this study, like IND 01, IND 3, and ARC 05, they basically get not much going on in the drain. It could be sometimes during a lovely sunny day, the people just washing their cars on the street, so you get water flowed into the drainage network. So they will be on the bottom of our list for the further inspection, but the IND 05 and IND 13 is what we really need to look into. And also we check the flow duration of all of our discharge sites. And in terms of the median value, for the industrial activities, every single pulse tend to last no more than 51 minutes. And for residential and commercial site, every single pulse lasts roughly 45 minutes. So this basically tells you what we want to emphasize here is 75 of the pulses actually last no more than 90 minutes. And that basically explains why our previous detection methods, like visual inspections, they won't be able to detect most of these discharge activities. They just last for a very short of period of time. And if you're thinking about this, you have a large catchment, and you are expecting the field crews can be out there at the right time and right place. That's almost like a mission impossible. Even for our concept with the low-cost sensor army and real-time alarm, we now be able to get enough time to eliminate these discharges. So, we have to physically travel from our office out to the field and conduct all the, some kind of water quality indicator monitoring to understand, potential sources, and also have a crew of people actually searching all the upstream areas for finding these discharge events. So that's almost like, even with our sensor army, it is hard. So we ask ourselves this question: when should we inspect the site to capture the discharge activities with the information our sensor army can provide, with the information that previously you don't know? So here is the best outcome of this study. We call it the likelihood of urban dry weather discharges heat map. So every single cell here, the color representing the likelihood of you seeing dry weather discharge pulses at that specific time of that specific weekday. And the right boundary here basically shows you the typical work hours of work days. So basically between 6 a.m. and 6 p.m. between Monday to Friday. So IND05, the highest pulse number site we have detected in this study. You can see you got very high likelihood to seeing flowing dry weather discharges in the drain if you can visit the site during the work hours of work days. And if you want to ask me the trick, be there at 8 o'clock on a Tuesday morning. Every 2 times you go there, I think you will have 1 time that actually seeing very dirty water running inside the drain. And all of these kind of things also prove that these kind of discharge activities that highly linked to unauthorized drainage usage, linked to human-driven or industrial process-driven discharge activities. And also, we further look into this IND13, second largest number site. It looks pretty good, right? Pretty good people. They're doing nothing during the work hours of work days. Only, some tiny flows over there and over here. Well, they're just getting too smart. They know we tend to go out there in the afternoon and inspecting what they are doing. And they decide to run some pretty smart industrial processes and getting delayed. All of the water being discharged at almost like the midnight. So if you be there at a Saturday night at 11 p.m. and wait there until 1 a.m. on a Sunday morning, well, you will see something flowing there, and you better track back to the source to see what they are actually doing. There must be some dodgy things out there. So what we want to emphasize here, which is, with our local sensor army, we can really run all of this analyze online on our cloud computing backstage database. And, for our clients, for our industry partners like EPA, local city councils, we can provide them with this kind of information every week. So they can carry this kind of information and plan their next week ahead. And so basically they will know, okay, at Tuesday, I should go to IND05 in the early morning, and I should work late on a Saturday night, maybe just bring my kids out there, have a look what's going on at IND13. So I would like to conclude my presentation with this video that we basically found and at the upstream side of IND number 5 on a lovely Tuesday morning. Trust me, I've never seen such a bad discharge in my life. And we tested the water quality, basically everything, TSS, TPT, and E. coli, everything go above the roof. So in this case study, we basically proposed our low-cost distributed sensing army concept with our enhanced low-cost sensors, data loggers, and our installation methods. At Ojo's Quick, we trial our concept, and we detect lots of these potential illicit discharge activities in the network. I won't say all of them. I think I will only say all of them maybe next year back to you. When we finally eliminate all of these discharge activities, we will keep our sensors army in there for a little while to see whether we can still detect these dry weather discharge pulses. If they all discharge, if they all disappeared, I will tell you that that's the good news. We basically detect all of them, and we basically resolve this problem for the community. And also all the key information like the discharge frequency, duration, and specific discharge patterns we observed from this study, this kind of key information can be used to support the future detection work and the illicit discharge elimination. So before I come to the final end of this presentation, I would like to share with you some outlooks and or future visions. So more we look into our data loggers, sensors, and all of this concept, we think, illicit discharges detection is only one application. There are so many other opportunities like real-time monitoring of the drainage, monitoring like with the drainage network, sewer network, nature waterway systems, and also many real-time control applications with water-sensitive urban designs. So if you are interested in your work, we are already going much more beyond water level, temperature, and electrical conductivity sensors. Feel free to check our wiki page on our Boston team website and contact us, share with us with your crazy ideas. We want to collaborate with you. And all of our sensors, loggers, they're actually open source. So feel free to send us a message. We can ship some of these to you from our suppliers, and you can try it out to resolve the problem of your research questions. And finally, I would like to say I'm not the only one who enjoys sitting outside our lab playing with loggers and sensors. As electronic engineers sitting beside our biofilters and green walls. Without this strong team, with all my supervisors and our genius guys in our BOSO team, I won't be able to make this study. And finally, I would like to also send my special thanks to Australian Research Council for funding this project via the linkage program, and all of our industrial partners, including Melbourne Water, EPA Victoria, and North City Council for their ongoing support. Thank you so much. That's the end of my presentation.